we now have enough information using the Intro to NMR video that we can sketch NMR diagrams for the molecules we've been taking a look at. And so we're going to start with the one that contains the bromine. And we know how many peaks there are. There's going to be an A, a B, and a C. We know approximately the area under the curve. Well, we don't really know the area under the curve, but we know the relative ratio. And we're going to kind of sketch that. And we know approximately their chemical shift in ppm, and we know their splitting. So let's take a look at these. For peak A, we said that there are 6 of them, and they will be split into 2, and they will show up somewhere around 0.9. So I'm going to make a pretty tall peak. Around 0.9. And it's longer than that just because of it's a sketch. I said that for peak B, it's going to be split into 9 little peaklets. There are 2 of them, and it'll be between 1.5 and 2. So we'll call this one A. B. And I'm not actually counting all 9. I'm just sort of sketching that one. And the last peak, peak C, there's only 1 equivalent hydrogen. It'll be split into 2, and it'll be between 2 and 4. So that's an approximation of what we're looking at. So we can have a sense of what the NMR should look like before we actually run the experiment. So let's take a look at our second one. We know that there's 4 different types of hydrogen. There's a CH3, 2 different CH2s, and a hydrogen attached to the carboxylic acid. So for the one that we're calling A, and this one are also A peaks, it will have an integration of 3. It will be split into 3 because it's got 2 near neighbor hydrogens. And it's approximately at 0.9. Somewhere around there. The next one is there's 2 of them, and it is split into 6, and it's around 1.3. I'm going to sketch it and then add it. Shrink it down a little. Oh, let me try that again. And there's another one just like it, a little further upfield. And again, these are sketches. Because these are so much bigger than they would be in real life, they're going to run into each other. And then the last one is somewhere between 10 and 13. And it's not split at all. And I didn't even make my scale long enough. So it's going to be somewhere around here. So that's a sketch for that one. Pause the video and see what you can come up with for the next 2. Start the video again when you're ready to see the answers. All right, this is what I came up with for propane. It's split into 7 around 1.3. That's the one that only has 2 particles. And it's split into 3 for the 2 sets of CH3s on either end. if we looked at the integration for this one, it would be in a 3-to-1 ratio. So hopefully you can see how to sketch these, and being able to sketch them is really important for the next step where you're going to have to figure out how to identify what these are from spectra you've seen. All right, so let's take a look at this molecule and the spectrum that was run. So I'm going to draw in the hydrogen so you can see where they are. Here are my A's. There's my B. Here's my 2 C's. And my 3 D's. 1, 2, 3. And I have 1, 2, 3, 4 sets of peaks, and I have to identify these peaks. So let's start with the the ones that are CH3s. Those tend to be around 0.9 to 1, and so we're going to assign these to that. I didn't look at the integration. The integration would give it away. But let's look at the splitting. This peak is split into 2, meaning it has one near neighbor. Of my CH3s, that has a near neighbor. And those peaks seem to be bigger, so we're going to call this one A. That's called annotating your spectrum. The second one has 2 near neighbors, so it's split into 3. So we're going to call that peak D. Then we have to move to the other 2. We have peak B and peak C. They both look like they're split into 4, except the one that's around 2.6 really isn't. What's happening here is that the one that is split into 4 here and is slightly larger because there's twice as many, that's really split into 4, and that's peak C. This last one really should be split into 7, but look how close it is to the baseline. We're only seeing, actually, that's 5. We're seeing 5. There are 2 more that we can't see. That one goes to B. So what we've done is annotate the spectrum and the molecule so that we can match every peak to every hydrogen in the molecule. That's what you're going to need to do when you combine NMR and IR together. So this one is a little different because now we have integration telling us how many. So let's assign them A, B, C, and D. So I have 3 A hydrogens, 3 D hydrogens, 2 B hydrogens, 2 C hydrogens. Oh, how do I figure this out and where do I start? Well, first I'm going to start with my 3 hydrogens. One of them is split and one of them isn't. One of them is close to 0.9 and one isn't. The one that is close to 0.9 is going to be D. My reasoning is that it has 2 near neighbors, so it's going to be split into a triplet. And also, it is farther away from the electronegative oxygen, so it's going to be closer to its normal spot. It's going to be at the lower parts per million. that means the other one is going to be A. My rationale is there's no splitting because if I go to the next carbon over, it doesn't have any hydrogens. And it's very close to that electronegative oxygen, so it's going to be at a higher ppm. Then I'm looking at B, C, and D. And B and D, B and C, sorry. B is closer to the oxygen, so it's going to have higher ppm. Also, it's next to C. It's split into 3. So this one is B. The next one has to be C. And let's see if we can rationalize it. It's at lower ppm because it's farther away from the oxygen. And it has, let me do these in blue this time, 1, 2, 3, 4, 5 near neighbors. It has 1, 2, 3, 4, 5, 6 peaks. So that one has to be C. So what we can do is identify NMR and match the different peaks to a known structure. All right, this was a challenging one, but let's see if we can logic it out. I started with my 1 hydrogen. There's only one possibility. It's the aldehyde in the benzaldehyde, and it's going to be at the very high ppm because it's an aldehyde, the hydrogen attached to an aldehyde, and it's not split. It's only a single hydrogen. The next one I assigned was A, only one that has 3 hydrogens. Then I did E and F because benzene rings tend to show between 7 and 8. If you see parts per million between 7 and 8, it's almost always a benzene ring. And I said E was the one with the higher ppm because it was closer to the electronegative oxygen. So that gave me E and F. D I assigned because that's attached to the ether function. And then C and B should be very close to each other, but I said C was slightly higher because it's slightly closer to the electronegative oxygen.